Hello, and I'm now showing my first lab of the real-time rendering. First of all, is phone illumination. This illumination is consists of three main parts: ambient, diffuse, and specular. And you can see this is my teapot model, and it is rendering by the phone illumination. Yes. And first of all, we already processed the material. And in these materials, I have Ka, Kd, Ke, etc., which means the material properties, and they are actually the RGBA data. When processing with the ambient, um, we only need to use the color of the surface to multiply the value of the ambient parameters, and which is ambient parameters is Ka. And secondly, for the diffuse, it is based on the light position. We can use the picture above to calculate the cosine value between the light position, light direction, and the normal of the surface. After getting the angle, I can use the parameter here, which is angle, color of the light source, diffuse properties, and the color of the surface to get the diffuse I want. Finally is the specular. We first need the direction from the light source to the object. Secondly is the normal. If I get a normal and the light source, I can get the reflected light. After getting the reflected light, I can use the camera position to calculate the reflected to calculate the angle between the reflected light and the camera position. And using the corresponding materials over here, and it is actually similar to the diffuse, we can calculate the specular color. And the sum of these three parameters, which is ambient, diffuse, and specular, and then I can get the phone illumination. The second one is the photorealistic technique, gauge technique, and this is the realization of this technique in my scene and to the teapot model. Okay, and the realization of this technique is really similar to the phone illumination. In this part, I will not change the ambient and the specular part. However, I will change the part of diffuse. First, it is necessary to calculate the angle between the normal and of the surface and the light direction to the surface. Then I will get the cosine angle. Using the methods of using the method of linear interpolation, I can change the color of the surface based on the cosine angle I just calculated. The closer the normal and the light direction, the warmer the color will be, and vice versa. Getting the color of the surface, which is calculated by the linear interpolation, I finished the gauge technique. And the side, the side facing the light has a warm color, and the side facing the backlight has a cooler color. Finally, I realized the model of Cook-Torrance model. And the Cook-Torrance model is a physical-based rendering model for calculating surface illumination that simulates the effect of light interacting with rough surface. The model is especially suitable for rendering metal and non-metallic materials, and this is the teapot I used the Cook-Torrance model to realize. And you can see the specific reflected. Okay, and then it's time for us to discuss about the fragment shader. First, You can see this part of the code. It is all about the parameters which may need in the calculation of the Cook torrents. And I would like to talk about this FC parameters, which is the Fresnel reflectance. Using the linear interpolate, the more metallic and the FZ parameters will more close to the gray color. So what's the point? The point is that vector 3 0.04 is kind of numbers that represent the surface become non-metallic, and the gray color is the color of our surface. So the so using the linear interpolate, I can use the uniform metallic to decide the surface. Is that non-metallic or gray color, which means more closer to the metallic? And then the color direction and half vector. The half vector will be used uh, in the normal distribution function that I will mention later. And yeah, I would like to talk about this attenuation. In normally, attenuation is 1 divide the square of the distance. But I found that in this situation, divide the square of the distance may lead to the model become too dark because the light attenuation is too big. So in this case, I just use distance to decide the attenuation, which looks better. And the model is not too dark. Yes, it performs well in this case. Then I will do some explanation of the cotorrance BRDF. And first, I'm going to talk about the normal distribution function, which we call it NDF. This function is used to calculate the normal distribution of the microfacets, and it is used to describe how the roughness is going to affect the reflectance. And we are actually using this formula to get the parameters we need. And the alpha here is the square of the roughness, and yes, the parameters left is the dot product of the surface normals and the half vectors. After we get the normal distribution function result we want, then we are going to the geometric function. And this is actually used to calculate how does the bump block the path of the light. There is 2 ways of this process, which is light to the surface and the surface to the observer. So yeah, the viewer and the light source, and the result of the geometric of this function is used to calculate the direction from the view and the light to calculate the geometric shading and collision effects. And it is actually using this formula to finish these two function. Yeah, you can see that it is actually the same. So, and then after we getting the 2 parameters we want, it's time we are going to talk about the Fresnel function. And this is actually used to calculate the proportions of light reflected at different viewing angles. And the interesting point is that the result of this function actually will be useful in calculating both diffuse and specular. And this is actually realized by this formula. By using this formula we can get this, it's actually the same. Okay, after we get the Cook-Torres BRDF calculations, we can get the we can get the 3 parameters we want. And then I can use the parameters to calculate the specular component. Since in Cook-Torrance model, the the diffuse and specular is actually related to each other. Because if the model become more metallitic, which means the specular will become stronger, and the the diffuse will become less, and this is and vice versa. So okay, based on this rule, I can get the Ks and Kd, which is specular and the diffuse component. And using this function, I can, because the specular is actually calculated by the normal camera view and the light sources, and I can actually using this formula to get the specular I want. And then back to the principle I mentioned just earlier is that the diffuse and the specular is related in this model. So I can actually using this model, this formula to get the final result of the outgoing radiance with diffuse and specular components. And yeah, this is the result affected by these two parameters. After I getting the outgoing radiance calculated by diffuse and specular components, I can do the final step, calculating the ambient component. And this is the ambient component is the result of the surface light of the teapot times the ambient occlusion, which I define, which the AO is the ambient occlusion, and it is actually the uniform data, and I define it in the main C++ file, which is here. I set the environment shadow to the 0.5 in this case. So after I get the ambient, the diffuse, and the specular components, I can sum them up to get the final colors of the text of the teapot. And there is two steps below, and these two steps is actually the tone mapping and the gamma correction. And tone mapping compress bright colors so they fit on my screen, and the gamma correction adjusts colors to make the scene and the color of the surface become more nature. And after these two process, I can set the fragment color of the teapot, and that's how I realized the Cook Torrance model.